Welcome to M8307 Numerical Analysis class. In this lecture, we are going to introduce numerical methods for PDEs. Previously, we've learned to find numerical solutions to ordinary differential equations. Now we direct our attention to learning methods of finding numerical solutions in some partial differential equations with only one approach maybe. Let us first recall partial differential equations. When taking the partial derivative of this function, this multivariable function, with respect to x, we act as if y is a constant and take the derivative with respect to x alone. Similarly, derivative with respect to y can be found. So partial derivatives with respect to x and y are respectively denoted by the partial derivative of x with this partial sign, and also the subscript of x, subscript x of f, and also subscript x of z, for example. These are the ways to show the partial derivatives. And also for the y derivative, we can also do the same thing. So these are how we denote derivatives, partial derivatives. An example, let's consider this multivariable function. And then following the partial derivatives, partial derivatives can be found. So the partial derivative with respect to x can be found by here 2x plus 2y, because y is just y will act just like a constant, so this will be 2y, and here this will be negative y to the fourth. So this will be the x derivative, the x partial derivative of f. And also the y partial derivative of f will be 0 on this term because there is no y here, and x will act as a constant, so this will be 0. And here we will have 2x, and there this will be negative 4xy cubed. So here. Okay, what about mixed derivatives? So we take the x derivative first and then take the y derivative second. So this can be obtained by, for example, with this expression. So if we take the y derivative here on the both sides, this will disappear and this will be 2, and there will be 4y cubed here. So 2 minus 4y cubed. Okay, we can similarly obtain the same thing by taking the x derivative on this expression. So when we take the x derivative, this will be 2 minus 4y cubed, which is the same. Yeah. Okay. There's a theorem to give you an idea about the mixed partial derivatives, either the order of the mixed partial derivatives, but it's beyond the scope of this course. So we just take the derivative with the given order, and this will give us the partial derivative we need. Okay. Also, for example, if we take 3 times this mixed derivative plus the y derivative plus twice the x derivative, we obtain this equality. Okay, so this is a partial differential equation because this is an equation involving partial derivatives. So this makes this equation as a partial differential equation, and this has a solution f of x comma y is equal to x squared plus 2xy minus x y to the fourth, because this is this is a function that will satisfy this equation already. We say a solution instead of the solution because this partial differential equation might have more than one solution. Actually, it will have infinitely many solutions in reality. Okay, PDEs might be models of physical phenomena that we might encounter in real life. Okay, so for example, a PDE known as the heat equation models the temperature distribution in an environment. This equation has to be equipped with an initial condition and some sort of boundary condition or conditions. Okay, an example, consider a uniform rod of length 1 with non-uniform temperature lying on the x-axis from x equals 0 to x equals 1. So we have a rod with non-uniform temperature. Suppose the initial temperature of the rod and its temperature at the endpoints are known, then one can find the temperature by solving this PDE. Okay, so we have given a rod like, oh, let's make it more flat. No, I cannot do that. Okay, so here, and these are the endpoints. We have given the temperature values at the endpoints, which is x equals 0 and x equals 1. And also we are given the initial temperature distribution. Okay, so we are trying to find the temperature at a point at any time in the time, basically. Okay, so this will be the partial differential equation, and this will correspond to the initial value as if t is equal to 0. We are given a function which will be corresponding to the temperature distribution initially. Okay, so this is initial temperature distribution, and T0 T will be equal to TLT. This is the temperature at the left end point or for any given time. And here we are given T1 T, which is the temperature at the right end point here at any time T. So this is TRT. Okay, so this is a PDE with an initial value and two boundary values. Okay, while solving ODEs, we have divided time interval into small pieces, like sub-intervals, and found the values of the unknown function in these partitions. And similarly, we can find solution for PDEs by taking subdivisions in the space as well. Okay, consider the equal space points 0k, 2k, and all the way up to nk is equal to 1 in the time interval. So we are subdividing the time interval 0, 1 like with this equal space points. Similarly, we can do the same for spatial domain like 0, h, 2h, and so on, like all the way up to 1 with a uniform mesh size h. Okay, so we use a step size for the time interval like k and mesh size h in the spatial domain, and we are basically subdividing both domains, both in time and in space. Okay, let's also say Tij is an approximation to the temperature at the point xi and time tj. Okay, this is an approximation to the solution at the point xi in space and tj in time. Okay, so this is this is the approximate solution. Okay, then we can use this subdivisions together with derivative approximations to obtain a discrete approximation to the original PDEs. Consider the following approximations of derivatives. Okay, so the time derivative can be approximated by this formulation. So this the superscripts are standing for the time time interval. So here the difference between, if we fix the spatial variable, the spatial point, and take the difference between two subsequent time intervals, solutions at two subsequent time, then dividing by this by k will give us the time derivative at xi and tj. This is basically an approximation. And also we have the second derivative in the spatial variable x, so we can use the central difference for that goal. So the central difference formula is given in this way. So we fix the time j, okay, and we vary the indexes in the spatial variable because we are taking the derivative with respect to the spatial variable. And in this particular case, we will have h squared because the mesh size is h. Okay, so this is the derivative with respect to time, and this will be an approximation to the derivative with the second derivative with respect to the spatial variable. So we can substitute these two in this equation, and we obtain this equality indeed, but this is just an approximation, and this will be a discrete form of the given PD. Okay, we cannot solve this equation immediately because we still need some informations to start this iterations. For example, what is, for example, T0 values or TI 0 values, right? Because the previous values are always needed. So what are they? The given initial value Tx0 is T naught x. This is the initial temperature distribution, and this is given. So we can use this to find Ti 0 values by simply substituting xi in this formulation, okay, in this function. So T0 xi will correspond to Ti0 immediately. So we can find this values before even starting to iterate or use this equation to find an approximation. These are already given. Also, the boundary values are given at the end points. So we can assign them to the corresponding unknown. So TL, TJ values will be T0J approximations, but these are indeed exact because these are from the given information, and the given information is already exact. So T0J can be found using this function, and T and J can be found by TRTJ. Okay, so these are from the problem data. Okay, this algorithm is similar to building a skyscraper that gradually rises as one floor is built. A constructor moves on to the next. If we, for example, if we consider the given the given data and what is not known, we obtain the squares. These are already known because the boundary values at the left endpoints are given at any time. So this is the time scale. So if we move up, that means we are moving in time. We are marching in time. From left to the right, we are changing the spatial variable. So this is our spatial variable. So these are the time variable, and the time at the left, the temperature at the left endpoint are known. So all the time levels, we have the left endpoint value, so the squares will appear there. And also we know the right endpoints, the temperature at the right endpoints anytime. So these are also known, and we also know the temperature distribution initial. Okay, so all these squares are known, and using these squares, we need to find these circles. This is like building a skyscraper. So if we are given, if we start this algorithm, if we start use the previous algorithm, that means we are given all this information, and we are at this level. For example, using the information from this level, we can find the values of the temperature at T1 level. Okay, so once we know the temperature at this level, we can move one step up. Okay, so for example, if we know the values, the temperature at time is equal to Tj minus 1, we can find the temperature at the time is equal to Tj, and then using this again we can move on move one step up, and this will be like we gain elevation. Okay, so we basically we start with the ground level, and then first level, second level, and so on. So this will be gradually rises that we can find the solutions gradually. Okay, that's something that's here. These comments are the thing that I already mentioned here, so I will skip that. An example, find an approximation to the solution of the following heat equation with 100 equispaced mesh points and uniform time step size k is equal to 0.001 at the final time t is equal to 5. So this is the heat equation we need to solve. So this is very similar to the one we just solved. And also here the initial temperature will be equal to 5, and at the left end point temperature is equal to 15, and at the right hand point the temperature is 10. So we need to solve this PDE, this heat equation, to get the temperature at time is equal to 5. Okay, so the Matlab code is given for that. This is the spatial variables. So the left endpoint in the space is equal to 0, and right endpoint will be equal to 1. N is equal to 101, which is the number of mesh points in the space, and H will be equal to right endpoint minus the left endpoint divided by the number of subintervals. So this will be n minus 1, so we can find H this way. And the mesh points, the node points in the space will be starting from 0 and going all the way up to 1 with H increments. So this will give us the vector of spatial node points. For the temporal variable, we have t0 is equal to 0, or initially we are at time is equal to 0, and we are trying to find the solution at time is equal to 5. Say k is equal to 0.001, and this is also given. So the time variables will be 0k, 2k, 3k, and so on, and this is the vector of time variables. Okay, so initial and boundary values can be also set in this way. So tj is equal to ones of the vector of ones from 1 to n. So this is size of n. This is the vector of size n with ones, and we multiply this by 5 to get the initial temperature distribution, and we know the temperature is 5 everywhere initially, and the T left will be equal to 15, the temperature at the left end point, and T right will be 10. This is the temperature at the right end point. Okay, rho is the heat transfer coefficient, and this is equal to 0.05. So 0.05, it is from here. And we define S to be equal to rho times K over H squared. This is just, if we go to the algorithm and we multiply both sides by K, this will be K times rho over H squared. And for simplicity, we set S is equal to K times rho over H squared, and solve this expression for Tij plus 1. Okay, when we do that, S will be equal to that. This is for just for simplicity. Tj plus 1 will be zeros, with the vector of zeros with n mesh points. So this is just for allocation purposes. Nothing just happened here. So this is just zeros now, but we will update this tj plus 1 values. Okay, the algorithm for the loop over the time steps, j will start from 2 to the length of t. So we will have length of t much time steps, and for the spatial loop we have for I from 1 to n is the number of the spatial nodes, and we say if I is equal to 1, then we are at the left endpoint. We need to set tj plus 1 I is equal to the left to the temperature at the left endpoint. So this is already known, so we know we don't need to have any computation for that. Or if I is equal to n, this means we are at the right end point, so we know the temperature value at the right end point, so we can immediately update that value. But if I is not equal to 1 or not equal to n, then we jump on to the else case. So in this particular case, we need to apply that algorithm. So this algorithm, okay, this is identical with that already, okay. So doing that, we can obtain solutions, and these are the updates for the solution. Okay, so each time level, once we get the solution, we update the solution with the previous one and move on to the next step. Okay, and this is the plot. When we apply this algorithm, we know at t is equal to 0, temperature is equal to 5 everywhere from 0 to 1, and at the endpoints they are 15 on the left and 10 on the right, but we cannot see the points there, just that points. These are the values. When t is equal to 1, this will be the temperature distribution. For example, if you consider the temperature at 5.5, it will be around 7 at time is equal to 1. And when time is equal to 2, we get a solution like that. So for example, if you consider 0.6, the 0.6 in the space, the temperature will be close to 8.5, okay. And then when t is equal to 3, temperature is rising in the interior of the domain and decreasing. Actually, it's also rising here, but it's like gaining temperature from the left and right endpoints. So this will be like when t is equal to 5, this will get closer and closer to a line segment. Okay, so this is an equilibrium. This will be the line segment will be the equilibrium solution for this heat equation. But the point here is we can use our discretization for derivatives to get an approximation for PD, for solution of the PD. Okay, notice that this algorithm, in this algorithm, the forward Euler method is employed for the time derivative. So we on the right hand side and on the, the on the terms that are not involved in the derivative, we use the previous time level. But instead, we could use the current time level as well in the right hand side forcing functions, for example. Okay, so when we do that, this will give us an equatorial time discretization and center difference in the space. So, okay, in this case, we need to use values of the right-hand side terms at the very same time level at which we are seeking the solution. So this is the idea. Okay, that results in additional complexity to the implementation of the method. So this is the an example for that. So here we use the tj plus 1 time level on the terms that are not involved in the derivative of the derivative with respect to time. So here we have tj plus 1 instead of tj. If you consider the last approximation here, so the algorithm here, this was tj because we have worked with forward Euler time discretization here. But if we use backward Euler, this has to be tj plus 1. So when we do tj plus 1, if we use the solutions from the tj plus 1 time level, this will give us backward Euler method, but this will also come with some additional complexity. In this case, we cannot find approximations as simple as before. However, we may we may have to use this method for stability reasons. Also, this is something, the stability is something that we desire, and the backward order method is much more stable, or the backward order method will give us stable results. So we desire to use backward Euler method in particular cases, but this will be beyond the scope of this course. If we denote again s is equal to pk divided by h squared and solve this problem for the unknowns, then we obtain this equation. So here we see these are from the next level, right? Next time level, and this is from the previous time level, and these are all unknown. So 1, 2, 3 unknown appears in this equation. So this means in each equation we have 3 unknowns, and all these 3 unknowns are somewhat connected to one another. So this requires to use some linear system to get solutions. Okay, so we have unknowns, and these unknowns are just 3 of them here appearing. But if you consider this equation, this algorithm as a whole, then this will be there will be much more than 3 unknowns. So there will be a vector of unknowns. So this will give us a linear system to get the solution. So in this last algorithm, the size of the system matrix, by system matrix, I mean we will at the end of the day we will end up with a system matrix because we have more than one unknown. So this will be a system of equations like ax equals b. So as the value of h gets smaller, then the size of the system matrix will grow. Okay, so for example, if say h is equal to 10 to the negative 3, then the dimension of the matrix in this particular case will be 1000 by 1000. Okay, if h is, for example, 10 to the negative 6, then the dimension of the matrix will be 1 million by 1 million. Okay, so this means decreasing h values will increase the size of the system matrix, and increasing the size of system matrix will require much computational resources like time and memory. Or also, choosing small values of h increases the spatial accuracy. That's also true. If we choose h smaller, then as we know, as h gets smaller and smaller, the error will decrease proportional to h, the h squared in this particular case, because we are using center difference and this is second order accurate. But that comes with a price, very high dimensional system matrix. Also, the smaller the value of k, the more iteration number in time will increase. So if we shrink the k values, this will be the step size in the time, and space time. If we shrink that value, this means we need much more iterations to arrive at the final time. Okay, so that will also increase the computational complexity. and computational effort, which means more souls of the assigned system is required. Okay, that will conclude our lecture here, also our course here. Thanks for paying enough attention on this course and watching videos carefully and completing your assignments in time.